Okay, so apparently there are these blue-looking kilonova-sized explosions that are being observed, and apparently coming from just absolutely like nowhere. Like it looks like they're coming from, you know, well, there are some that look like they're coming from the centers of galaxies, and then there's some that appear to be coming from nowhere. We don't observe a galaxy where this comes from, and so this seems interesting to us. This doesn't seem to make sense. Why would these big, massive, emissions, high energy emissions, basically be just appearing in the middle of nowhere? And to me, this points towards my theory, because we do see some points where it looks like it's coming from somewhere. And I don't know if that's just because there just happens to be some overlap there. And so we observe them, but we just happen to observe them in, like, they're not actually coming from there. It just looks like they're coming from there. They're actually coming from behind it. That's potentially an option. It could also be that that's not what's happening and they actually are just coming from that spot. But if we know that that's a source and that's where they should be coming from, but we don't see a universe for other ones that have similar behavior, then to me, this points towards, my theory of, basically a curved universe, in that some things are over the horizon for us, and so they have not made it to us yet. However, they cannot make it to us. Maybe not that they have not, but they cannot make it to us. Like, their light just isn't able to reach us. However, if it's high enough energy, then it can reach us, and it does. And this is what we observe as these large flashes in apparently nowhere, right? Because the actual reality is that it did come from a universe. We just can't see the universe it came from, but this emission was high enough energy to, overpower the curve of our universe. And so we could see it over the horizon, even though, the rest of the universe is hidden. And I think this would be akin to, if there was a massive flash out on the horizon. Like, imagine if you were on a boat and you went out far enough that you were basically right on the horizon, and you shined like a really bright light or something towards me on the shore. I don't think I would be able to make out your boat, but I would be able to notice the bright light, is my theory. However, I got no proof for that because, obviously I'm not doing that experiment, but if someone wanted to, they could. I have a theory. That's my theory. I think it would work, but it doesn't really matter. Anyway, bigger stars, shorter lifetime matches with atomic behavior, more mass, less stable. So I'm actually bringing up a couple things here. There's mention of, I guess these explosions are coming from very large, red giants or something, maybe. I'm not sure. I watched this video a week or two ago, and I made the notes, so I assumed that I was going to make the video quick, and so I didn't put enough context, I guess. But bigger stars, shorter lifetime matches with atomic behavior, more mass, less stable, radioactive decay takes place. So what I'm saying here is that we know that stars that have more mass tend to have shorter lifetimes. And this makes sense with my photon theory because, more mass typically means less velocity, and then therefore less overall energy, and therefore, the red photons or red stars lose their energy faster than that of, a blue star or, a low mass star. And so, as I said, because it has more mass, it's less stable, radioactive decay takes place, and that's what we see as these kilonova explosions or supernovas or whatever. And so More mass equals less velocity and technically lower energy, which again plays in with my photon thing. So another thing here, like I'm really just hitting multiple points. This must have been like multiple things that I noticed in one video. The video was an Astrum video talking about these kilonova explosions. So look up that and you might find the video that I'm, kind of talking about this all from. But the fact that the stars form in star clusters, and then travel out aligns with my theory too. The Milky Way. So the fact that like stars don't just like randomly appear in spots, but there's actually like known cluster locations where they form and then they somehow get launched out. To me, this points towards my theory of how stars work as well, because they are born in a star cluster and then they get launched out and they go do their own thing and they gain mass and they gain, whatever, and they have their, like, so our sun has a solar system, right? And then so, it's doing its thing. Eventually it's going to die though, right? And so potentially, when it dies, what'll actually happen is that it'll give off a supernova explosion. It won't totally annihilate. It'll still have either a small mass, like be like a white dwarf or whatever, and it'll start to move back towards wherever it was born at. I don't know if there's any way we could find evidence to prove that motion happening. I don't think we have enough data to track that, because this would be on, I don't know, how long is it going to take for the sun? Millions, potentially billions of years, like timeline that we're looking at here. So I don't think we have enough data to track to know whether or not this would be the case. But because whatever motion is currently taking place would just be so negligible in the grand scheme of the motion, potentially, maybe not. But I think that if we kept watching the stars for another million years, we might be able to piece this together. So we just gotta be patient. So the fact that stars form in star clusters and then travel out aligns with my theory too. The Milky Way's stellar halo looks like a simple atomic electron cloud and would imply that our galaxy is low in complexity and mass. So I personally think that, galaxies are probably either atoms or I think initially I was like black holes or atoms, but I think we gotta scale it up. Black holes could be like protons potentially, but like an actual atom is like is probably most likely actually just like a galaxy. Like a galaxy is the scales that we're working with here, and that's why we see like cosmic web, connections between galaxies and stuff. And it seems like there's galaxy clusters, and that would be molecules, right? So we have atoms and then there's molecules. And so these molecules are potentially like galaxy clusters. And I think I have a video that's going to talk about that, because I think that there's some actual evidence towards that being the case now, which is awesome. And so I'll talk about it in the next one though, but I'll show you this quick image that's from that video. So like I said, you probably should watch that video, but you could see like that, like, kind of outline around our thing that looks very similar. Like it's just in like an ellipse, or, what is the proper term for a 3D ellipse? I have no idea. But it's like a squashed sphere, basically. That's what we're gonna go with. And so that looks very similar to just a relatively simple electron cloud, right? And if stars are what I think they are and stuff, then all the electrons would be within the cloud, right? And so there's a high probability chance that they would be in there, and what do you know, they are, right? And so anyway, less massive stars travel farther to higher energy orbitals before collapse back down, right? So what I'm saying here is that stars that are larger have shorter lifetimes because they have shorter lifetimes, they travel shorter distances before they reach, their point where they go supernova. And so they travel a shorter distance and therefore are in what we would consider as a lower energy orbital, because their max range is shorter than that of a star that can live a longer time, because if it can live a longer time, it can also travel a farther distance. Sorry. If it can live a longer time, it can travel a farther distance and therefore reaches what we would consider a higher energy orbital. And so it makes sense with my theory. Kind of, right? And so the Tasmanian Devil event, again, you should probably watch this Astron video. It'll give you context for what I'm talking about. The Tasmanian Devil event is interesting, but I think it also can point to my theory of stars effectively having energy orbitals. While most stars have energy and release it, there is the possibility to excite multiple electrons at a time, and this could be what happened. The atom or galaxy or whatever came into a high concentration of energy orbitals, a bizarre alignment of electron emissions at one time in which they all, so it could either have been that like the universe got exposed to high amounts of energy at once, or it could just be that they somehow all the quote unquote electrons or stars lined up. They just happened to line up with their emissions at that one time, right? And it could be that it was both, right? Because it came into contact with a lot of energy, they all simultaneously, went kilonova, or supernova or whatever, they went kaput. And so what this Tasmanian Devil event is basically multiple of these, high energy things popping off all at within a short time span, just a few minutes. We ended up receiving from seemingly the same location, just a ton of these emissions all at once, right? And so to me, it would make sense that, if you beamed an atom or a molecule with a lot of energy, you hit it with a high concentration of photons, you're going to see a high concentration of photons released from that molecule, because all of its electrons get excited, right? So long as it's a high enough energy to do so. And so, we would expect that to be the case in an atom, and I think we should be able to expect it to be the case in a galaxy. And so while most stars have energy and release it, there is the possibility to excite multiple electrons at a time, and this could be what happened. The atom or galaxy or whatever came into a high concentration of energy orbitals, or a bizarre alignment of electron emissions at one time in which they all reach critical mass and release their energy at one time, resulting in different energy levels to the bursts in a short period of time, right? So all of these bursts are not of the same strength. And I think that would make sense because, if it's multiple different orbitals of energy that are releasing all at the same time, right? If an atom gets hit by a white light, but it emits on multiple different parts of the spectrum, like green, blue, red, orange, it's going to emit all of those colors all together, right? And since and you wouldn't think that that's strange, right? You would expect to see that because it got hit with a high concentration of energy on all quote unquote wavelengths. And so I think potentially what this kilonova, this Tasmanian Devil event is just that, but on a galactic scale, and again puts potential proof towards my theory of us being very small. And so, the other event that's mentioned in this video or another one of them is the Finch observation having no gamma wave burst makes sense as it appears to be in the middle of nowhere, which we wouldn't expect. However, the blue appearance, the lack of gamma burst, being in the middle of nothing all makes sense in my theory and points to this being an event much farther away than anticipated. So this is what I was talking about initially at the start of this video, about one being in the middle of nowhere, right? So this one should have gamma waves to it, but it doesn't, and I think the reason why it doesn't is because the gamma waves have all been redshifted into, basically blue light, or like they've been shifted down in the spectrum. So we no longer observe gamma rays from this because the gamma rays have lost energy by the time they reach it to us, so now they're no longer gamma rays. And so, it appears to be in the middle of nowhere, which we wouldn't expect in classical thinking, but in my theory, the blue appearance, the lack of gamma bursts, being in the middle of nothing makes sense in my theory and points to this being a much farther away than anticipated. The galaxy from which it occurs is outside our view, and the majority of light is beyond the stellar horizon. Only this burst of light was bright enough or had enough energy to reach us, right? And so it's lost its gamma part of its spectrum because it's been redshifted, but it was able to reach us. However, the rest of its light is not of a high enough quality to reach us, right? So unless it's a really strong, high energy burst, we are not going to observe anything coming from this spot, right? And so potentially, if we kept an eye on where this came from, we could see another one of these bursts in the future from basically the same location, relatively the same location, so long as it happens in a somewhat near time frame. If we observe another one of these, which I would imagine we probably should observe another one coming from the exact same location within, I don't know, the next few years, realistically, it would make sense to have multiple explosions happening within like a decade to a century. But at the same time, maybe not. Maybe the timescales that we're working with, it's just way beyond our comprehension. So things are just extremely slow on the universal scale, even though we perceive these sorts of interactions as instantaneous on the atomic level. The magnitude of scale is just so insane that the time difference is also just so insane. And so that's actually an interesting experiment to do. That would be interesting to do. What was my interesting experiment? I just lost it. Do the order of magnitude, right? Figure out the order of magnitude that like an atom or an electron is, like, smaller than us. Like, its mass, like, figure out how many orders of magnitude it is smaller than us, right? And then figure out how many orders of magnitudes larger the galaxy is than us, right? And then see where that difference lies. And if it's relatively similar up and down, that's interesting. But if it's not exactly close, figure out, figure out how long, do from the electron all the way up to the galaxy scale, right? And figure out how long 1 second would be for, imagine, if you were at the electron's scale, imagine what 1 second would be, and then extrapolate it to the orders of magnitude of the universe, right? So basically, take 1 second at 10 to the, minus 30 something, right? And then whatever, I don't know what the orders of magnitude the galaxy is compared to us, but then multiply that number times, multiply 1 second times, 10 to the 30 whatever for whatever an electron or a photon is, and then, actually can't be a photon because apparently they're not a particle, but an electron, we'll do an electron. So actually, no, it makes more sense to do an atom. It has to be an atom, because according to my theory, that's what a galaxy should be. And so, do an atom, the orders of magnitude down to an atom, plus the orders of magnitude up to a galaxy. Sorry, I keep saying a universe. Up to a galaxy. Figure out what that orders of magnitude is, 10 to the probably, I don't know, 60 or whatever, right? And multiply 1 second by that number and see what you get. And I imagine it's going to be very big, and it won't be much of a mystery anymore why we don't observe such fast behavior for, we observe these things as quote unquote, I could probably do at least some of it. I don't know. Let's see if I could do it quick on this on my phone calculator. Usually gives a big number, and it's not like 1 times. We'll just do 10 to the 60 and see what happens. I never know what these buttons mean on this calculator. 10 to the 60. Yep. Okay. 10 to the 60 divided by. So we'll do a minute. And then divided by 60. So now we've got an hour divided by 24 divided by 365. It's just such an absurd number. I don't know if this is like an accurate orders of magnitude difference, but like 1 second to an electron, extrapolated up to like the galactic scale is like, I'm currently sitting at 3 years to the 50 times 10 to the 52nd. Let's see, what even is like, that's like, the number doesn't even mean anything. It's just so insanely large. Doesn't even mean anything, which the point I'm trying to get at is like, no duh, we see the electron as an instantaneous reaction, but meanwhile universes take millions to billions of years to do anything, right? What we observe as like, in 1 second an electron is emitting multiple times, potentially, right? Potentially, maybe not, right? But meanwhile, it's been millions of years and our star is, still shining. But in theory, the time that it took for our star to be born, fly out to where it is now, and then also, explode, go supernova, and die, right? All of that should happen instantaneously from, a greater perspective, which is just crazy because, that's all of our lives and plenty more. And it's just absolutely no time at all because time is relative. Like, there's no reason why that can't be the case. Time is relative. We're just dealing at different scales here. And so let's do divided by 1,000,000. Obviously, this is going to do nothing to the number, but yeah. I don't know. Like, the orders of magnitude, I don't know what the actual orders of magnitude are, so the number's probably maybe a little bit smaller than that, maybe it's not. But the point I'm trying to make is that if 1 second at that scale, if you are just doing a 1-to-1 translation, maybe it's not a 1-to-1 translation necessarily, but like 1 second there, when you extrapolate it out to the orders of magnitude larger that the universe, that the galaxy is compared to a single atom, it's just an insane number, right? It's just an insane amount of time. So yeah, I don't even know what I'm talking about anymore. I think I got everything in. That's why I kind of went on a ramble. I already kind of covered that why the Finch is potentially in the middle of nowhere. So I said that already, but I just think that this all makes sense. Like, none of this is unexpected for my theory. It actually all makes my theory make more sense. Whereas with the current understanding, these all make less sense, right? None of these interactions, these observations appear to break our current understanding. Meanwhile, they are just adding more reasoning as to why my theory works. And if you think that there's a flaw in my reasoning, let me know what it is. But I just think it's interesting that my potentially crazy theory is not harmed by this bizarre observation that breaks our physics. Not doesn't break our physics, but breaks our understanding, our current model of how the universe works, and all this stuff. Like, it breaks our current models of understanding. Meanwhile, mine is unharmed and strengthened. So I just think that that's an interesting correlation there. I just that's not the only one, of course. I have multiple things that can build off of this. Like, I'm not just like pulling this out of nothing. Like, almost everything that I watch is just like, yep, that made sense. Yep, that made sense. And I just think that that's really interesting. So, yeah. Peace out.